Okay. So, first, I've had these crazy allergies all day. I'm sorry. I promise it's just allergies. Yes.
Quick question. We're gonna get a new formula sheet for the test, right? So if we put marking.
These ones are yours to study with, to mark up, do whatever you want. And then for the test, I'll give you a fresh one. But at least you'll know what you'll have, right? And looks like I'll have lots of spares. So if you want more than one, go for it. I also posted the formula sheet under general resources down here at the bottom. So if you want the PDF, it's there as well. Last thing I wanted to point out here is I posted the logic handout. So I still have to make a video, just wasn't really feeling up to it today. And so hopefully tomorrow I'll make that logic video and I'll be using this logic handout. Okay? And so it's there, and then you can watch the video whenever you want. And I'll send out an announcement once I've posted it so that you know it's available. Okay? And then I'll see you again next Wednesday. Wow. To do more logic. Crazy. Okay. So what I did today, any questions before we start for today? So what I did for today is I wrote out the objective function as well as the constraints for each of the problems that I want to go through. Okay. I also, which as you know now from last day, it was just on Monday, I also, let's see if I can make this bigger, cheated. And we're not going to draw the graph together because that I think you're all comfortable doing, right? You're supposed to know how to do it. And you will have to do it on the test. But here, right, things I want to work on today, right, are finding the feasible set, right? Which region should I be in? Finding the vertices of the feasible set, and then maximizing or minimizing later the objective function. And so those three things are the ones I want to focus on. And on the test, you won't have the graph. No, no, no. I'll give you a grid, but not the lines. But I will give you the objective function, right? So I'll tell you whether you have to maximize it or minimize it, right? I'll give you the objective function. Notice that it's just x and y, right? And so what we said last day is I said, well, I need you to tell me what x represents and what y represents, right? So we'll do that today. And then subject to these constraints. Okay? Of course, these are all in here somewhere in this blurb, right? But I'm giving them to you, which I will do on the test as well. So that's nice. Okay. First, formula sheets. Two missing. It went to my junk, but and I don't know why. But I don't like it. So thank you. Okay. Nothing to it but to do it, I guess. Here we go. So we're doing maximization. A factory manufactures two types of gadgets, regular and premium. Each gadget requires the use of two operations, assembly and finishing. And there are at most 12 hours available for each operation. A regular gadget requires 1 hour of assembly and 2 hours of finishing, while a premium gadget needs 2 hours of assembly and 1 hour of finishing. Due to other restrictions, the company can make at most 7 gadgets per day. If a profit of $20 is realized for each regular gadget and $30 for a premium gadget, how many of each should be manufactured to maximize profit? If you don't know what a gadget is, it's just a thing. It's an unknown thing. So first, we have to figure out what X is representing and what Y is representing. So here, where X, and I guess I needed 2 lines, but I didn't give myself that. I only gave myself 1. The key is going to be here in this last line usually, because that's where we're given our objective function. And so then it makes it really clear with practice which is your X and which is your Y. So we're told that a profit of $20 is realized for each regular gadget. And so the profit is $20 times the number of regular gadgets. So then X must be the number of regular gadgets. And okay, I'm going to give myself just 1 more line here. Oh, too close. And Y is to confirm, and $30 for a premium gadget. So Y must be the number of premium gadgets. Now, what does each constraint map to? What's it representing? So we have regular and premium gadgets. That's great. We have assembly and finishing. And so a regular gadget requires 1 hour of assembly and 2 hours of finishing. So it looks to me, as I glance down here, this looks like the assembly constraint, and this looks like the finishing constraint. We'll confirm assembly and finishing. So a regular gadget requires 1 hour of assembly. Okay, that's here. And a premium gadget needs 2 hours of assembly. So that's here. So that looks good to me. And we have at most 12 hours for each of those operations. And so these two check out. Good. I think I skipped one. But, oh yeah, a premium gadget needs 2 hours of assembly and 1 hour of finishing. 2Y and 1Y. Good. Due to other restrictions, the company can make at most 7 gadgets a day. Right? Doesn't matter, regular, premium. So then X plus Y must be less than or equal to 7. And so this is the total must be less than 7. We also have this constraint here, right? I need to produce a positive number of gadgets, right? Or 0. I'm allowed to do 0. Yeah, that's an option. And must produce a positive number of gadgets. From these constraints, I know that you know how to draw these lines. Here they are. Ta-da! Pre-baked. I even kept the labels. So the red line is the x plus 2y equals 12 here. The blue line is the 2x plus y equals 12, and the green line is x plus y equals 7. Okay. We need to, and we just introduced this last day, and so that's why I want to spend time figuring out which area is in the feasible set, right? Which area satisfies these constraints? Now, these are all less than, right? And so usually what I do is I suspect that it'll be on kind of the downside down here, kind of the downside of each line. That's hard to do without practice, but we can tackle the x has to be greater than 0 and y has to be greater than 0, which means that in terms of our areas, I have to be in the positive x's and the positive y's. So it just restricts our area. Now what I would do to see which area satisfies each of those constraints is I would pick a point that's easy to work with, right, on one of the sides of the lines. I'm going to pick 2, 2 as my test point, right? So then I'm going to use x equals 2, y equals 2 in each of these equations, and I'm just going to make sure that they're true. Right? So I'll say 2, 2 as a test point. I need to add a page. So if I have these constraints, of course, 2 is greater than or equal to 0, and 2 is greater than or equal to 0. So that's how I know that those are in the right area. Okay. But I do want to look at these guys. Copy. Bless you. So we want to see, I'll space these out. Does 2 plus 2 times 2, is it less than or equal to 12? 2 plus 4 is 6. 6 is less than or equal to 12. Whee! Which means that that was the red line that we were working with, right? And so what that means is from this red line here, right, the test point is in the feasible set, right? It satisfies those constraints. And so I point my arrows down toward it. Good. So I suspect that all of these lines will have arrows down, right? We already kind of said that. But I want to give you, and if you feel comfortable doing just finding the arrows, right? I want you to show the arrows. Okay? But if you're comfortable just doing it, you don't have to use a test point, right? I'm just showing you a way that you can check to make sure. Okay? So then, let me do this one. So 2 and 2, well, 2 times 2 plus 2, is it less than or equal to 12? Well, again, That's 4 plus 2, which is 6, which is less than or equal to 12. So then if I 2x plus y, that's the blue line. Those arrows go this way as well. Finally, the green line. 2 and 2. 2 plus 2, is it less than or equal to 7? 4 is less than or equal to 7. So we're happy. So then finally for this green line, the arrow goes down as well. Right? Yeah.
Is there always going to be an x plus y is less than or equal to, or is one?
Just in this question. It's kind of common that there's a restriction on the total, but we'll see examples where it's not in there. Yeah, I think I have one where it jumps around. Yeah, like this example, there's a greater than and then less than's. So kind of, yeah, kind of all over the map. Yeah, so then you want to be really careful. Okay, so where's our feasible set then? All of these regions have to be satisfied at the same time. Okay? Which means that I'll start with kind of the easiest part, in my opinion, which is from our x equals 0, I'm going to move out until I hit a line. Right? And from our y equals 0, same thing, I'm going to move out until I hit a line. Right? For maximization problems, you usually just start at the origin. The next example, we don't do that, but we usually start at the origin, 0, 0, and then bloom out, and then we stop wherever we're fenced in. So then here, like that. And this is our feasible set. And although it's fun to color it in, I'll skip that for this one. It is fun though, isn't it? Okay. Now, why did we find the feasible set? Because our objective function, the profit, will be maximized at one of the vertices of the feasible set. Well, it's too loud. Okay, so we found our feasible set. Now we need to find the vertices. First, I want you to label the vertices. What's a color that I can use that's going to show up? Is light blue going to show up? Yeah, okay. I start at 0, 0. Right? And then I want you to work around clockwise. So here, B, C, D, and E. Couple more, or at least one more vertex in this example than we had last day. Okay, let's see here. Find the vertices. And like I said last day, if you've shown the work as you're drawing the lines, you can just say, see work above, right? If you have that intersection already. A is at 0, 0. I won't spend any time on that one. B, now it's nice to be able to look and confirm, but I will be looking for your work, right? I need to see that you know how to do it. Okay, that's what's important. So I suspect it'll be at 0, 6, right? But let's confirm. How do we confirm? Well, this is the intersection of x equals 0 and the red line, which is x plus 2y is equal to 12. Okay? So I'm going to write that out. B is the intersection of x equals 0 and x plus 2y is equal to 12. I think substitution in this case is going to be the easiest. X is 0, I plug in x is 0, solve for y, I get 6. Right? And so it's not too bad. X plus 2y is equal to 12. 0 plus 2y is equal to 12. So y must be 6. Therefore, the intersection is at 0, 6. How about C? C is the intersection of the red line and the green line. And so the red line is x plus 2y is equal to 12. And maybe I'll just write it here and then move it down. And the green line is x plus y is equal to 7. And it's the intersection, whoops. Intersection of those two lines. It's up to you how you want to find that intersection. You want to use elimination. There is kind of a nice option, right? You can eliminate your x's. I'll use substitution just because I like it. I like it. Let's see here. All right. So the intersection x plus y is equal to 7. In that one, I'm going to solve for x. X is 7 minus y, which I'm going to substitute into x plus 2y is equal to 12. So then I get, I'll start here at x plus 2y is equal to 12, where x is now replaced by 7 minus y. So I get 7 minus y. Be sure that you use brackets. It's one thing until you feel comfortable expanding it. So I get 7 minus y plus 2y, which puts me at 7 plus y is equal to 12. What's 12 minus 7? 5. So when y is 5, I'm going to cheat. I have x is 7 minus y. I know. I told you to put it into one of the originals, but it'll be the same. Fine, I'll do it properly. Substitute y equals 5 into x plus y is equal to 7. Cheeky. Then I get x plus 5 is equal to 7, so x must be 2. So therefore, the intersection is at 2, 5. Now, what's nice about having the graph is we can just check to confirm. Let's see. X is 2, Y is 5. Looks reasonable to me. How about D? Making us work for it. D is the intersection of the blue line now and the green line, which are next to each other here. So I'm just going to steal these and bring them down. So now D is the intersection of, I'll delete this, but 2x plus y is equal to 12 and x plus y is equal to 7. You can do the same thing again. The first equation is different. Right? Here it was x plus 2y is equal to 12 and x plus y is equal to 7. And now we have a slightly different 2x plus y is equal to 12, right? But the procedure will be the same. So I'm going to change it up a little bit because here I have y on its own. So I just want to substitute into the one that's on its own if I can, right? And so then I'm going to solve for y. Solve for y in x plus y is equal to 7. Then I get y is 7 minus x. And then substitute into 2x plus y is equal to 12. Then I get 2x plus 7 minus x is equal to 12. Same deal. 2x minus x puts me at x plus 7 is equal to 12. So again, x must be 12 minus 7. 5. Solving for y. Therefore, y is 7 minus 5. So y is 2. So the point is at 5, 2, which we can confirm way up here. X is 5, y is 2. Looks reasonable to me. Right. Finally, E. E is our blue line. Our blue line is the 2x plus y is equal to 12. And the equation of the y-axis, right, is, or x-axis is y equals 0. So 2x plus y is equal to 12. Okay. E is the intersection of 2x plus y is equal to 12 and y equals 0. So then I get 2x plus 0 is equal to 12. So then x must be 6. So then the point is at 6, 0, which again, we can confirm visually. Looks good. Oh. Feels like a lot of work because I have to say it all. But when you're just doing it, it's not too bad. Now what? Now we want to evaluate. Oh yeah, sorry. You got it. Now we need to evaluate the objective. Sorry. Let's do more. Evaluate the objective function at each of the vertices, right? Because that's how linear programming works. That's our fun fact that we're using, is that it will be maximized all the other points inside the feasible set, I should say that all those other points in the feasible set will also work, but they won't give you the maximum. And so they'll work, right? But only at the vertex. Oh, sorry, now I did it again. Will it be maximized? I'll start setting up my table. I like to set up a table. You don't have to, but it's a nice way to summarize it at the end. So my vertex, I'll start by A, B, C, D, E. E I know is 6, 0. Working my way up, 5, 2, 2, 5, 0, 6. And 0, 0. Yeah. There, in real life, no, there isn't a reason. The only reason is because I need to see that you know how to find the intersections, because it was a topic that we learned. That's the only reason. Yeah. So on the test, you have to. But if you're doing something like this in real life, no, you can just use Desmos, find them. Okay, let's see here. What was our objective function? Profit way back here is 20x plus 30y. So the profit is 20x plus 30y. My first option is usually not that good. Make 0 profit. At 0, 0, I don't do anything. It is an option, but it's never the maximum. 20 times 0 plus 30 times 6. 180, I guess. Twenty times 2 plus 30 times 5. I need you to whisper the answers louder. What's 30 times 5? 150 plus 40. 190. 190 is better than 180. So that's where things are looking up. How about x is 5 and y is 2? Get 160. Not as good. Or 20 times 6 plus 30 times 0. Looks like 120. That's the worst. Well, 0 is the worst one, I guess. So you have this list of possible profits that you could pick. Which one are you going to pick? You're going to pick C. Whee! Which means that you need to produce 2 regular gadgets and 5 premium gadgets. So here, this is your maximum. We would need to produce 2 regular gadgets, 2 regular, and I'll just say 5 premium gadgets. to maximize the profit to $190. Look at that. Squeeze it in just on that page. I'll scroll down because
Does it probably like just use the C point and avoid the table? Over here to show it in the test.
you have to show it.
It's gonna be a long time.
You have to show me that you know. That's your job. Show me all the things you know. If you're writing the test and you know, something happens, you can't remember where to start, okay? Then what I want you to do is just write what you would do, right? So, oh, if only I could draw these lines, I would figure out which area satisfies the constraints, find the vertices by finding the intersections, right? You can just tell me, because that you can memorize, right? You probably should if you're going to solve these problems, right? And so if you're ever finding that you're missing a piece because you can't remember how to do it, then always just tell me what you would do after, and then I can still give you some marks, right? Because that's worth something. Huh? So, good. Okay. And mostly out of curiosity, how long did that take? Oh, 40 minutes, almost. Yeah. This one? Oh, the graph, yeah, you bet. Yeah, it'll be faster because you can just do it at that point. But it'll be a good chunk of marks. I don't know exactly, but it's usually about 8 to 10 marks out of a 45 mark test, I would say. And so it is a good chunk of your marks. So it's really devastating. You can't do it. Okay. Oh, and sorry, you asked a second or a first part of that question. The question on the test would look like this, except not the blue, the blue, it's all blue, not the light blue parts. So the dark blues would be on there. Dark blues. And then from there, you're on your own. Yeah. You got it. Course. Of course. Yeah.
So the vertices are only the they lie within the feasible set.
Yeah. Yeah. So you're looking for the corners of the feasible set only. Yeah.
I have a question.
Yeah.
How do we solve it?
D is
Like what's the what y here is 7 minus x.
Yeah.
2x plus y instead of yx. Don't understand where the x is and where 2x.
let's go back there for D. So in x plus y equals 7, I chose to solve for y. mostly because I see a lonesome y here and it makes it a little bit easier. 7 minus x is, let me do that. So 2x plus 7 minus x puts me at 2x minus x, which is x, and then plus 7 is equal to 12.
And you need both of those formulas, I guess. The
Equations?
exact one. You need both of them because both of those equations were crossed between each other, right?
Yeah, so you want to pick the ones that create the intersection. Right? And so that's why they're different depending on the intersection.
So basically you move x into 2x and subtracted it from it, so it becomes.
Yeah, totally. Exactly. Nice. Good. I think it's funny that this one is the third example because it's probably the easiest one. The only weird thing about it, and I say it's the easiest because they give us the graph. It's the weirdest because we have this line at x plus y equals 1, kind of chopping off our 0, 0, which is usually in our feasible set. It even gives us the vertices. Let's call this A, B, C, D, and E. Let's see here. I'll try to do kind of color-coded, sort of at least. So we can talk about different colors of lines, hopefully. But because we already have the vertices, it's not so bad. So this question just says, solve the following maximization problem graphically, which is how we do it. We want to maximize P, which is 10x plus 15y. We have the constraints. So x plus y is greater than or equal to 1. Now, the greater than puts me on the top side of the line, right? Which is why in our feasible set here, right? This is our feasible set. We have this x plus y equals 1, and we have to be above the line. Right? Now you could try this question and make sure that your graph matches what they gave us, right? And make sure that your vertices match what we're given, right? But because we have them, we're just gonna do it. Because I also want to do some minimization problems. Don't worry, they're the same. Right? Except at the very, very, very end, you're looking for the minimum, not the maximum. So if we have our vertex, oops, A, B, C, D, E, A is at 0, 1, B is at 0, 3, C is at 2, 2, D is at 3, 0, and E is at 1, 0. And we want to maximize P equals 10x plus 15y. P equals 10x plus 15y. At A, whoops, nope, x is 0. Tried to do 1, that would mess us up. And y is 1, so I get 15. At B, 10 times 0 plus 15 times 3, 45. 10 times 2 plus 15 times 2, 50. I know you can't do that to me. I was feeling good about my 50, but I wait for you. 10 times 3 plus 15 times 0. Love all these zeros. And 10 times 1, 15 times 0. Given a choice, I choose 50. We were told to maximize, right? And so here, that's the key. If we were asked to minimize, then you would pick the smallest, right? So it depends. And so we want to maximize, which means, hey, it's C again. Huh? Quirky. And this is the maximum. Therefore, P is maximized to 50. We don't know the units, so that's okay. But when x equals 2 and y equals 2. And we don't know what x or y are either. If we did, it would be nice if you could articulate what they are. But I've already made you do it as part of the question earlier, so you don't have to, but it's nice to show up. That's your job. Show off all your knowledge. Okay. Any questions about that one? Yeah. Then let's do some minimization problems, right? Like I said, we solve them the same way. A difference that we'll find is that often the feasible set kind of starts, if we go back to maybe this graph here, often for minimization problems, okay, the feasible set will start kind of at the outer edge of the lines and then work its way out to infinity, right? So it just kind of goes out, 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 right? That's the difference. So that's kind of a more difficult feasible set to work with, in my opinion, but we can do it. On the plus side, there's usually fewer vertices, so it's kind of a give and take. Okay. So, and one thing, it won't be the case for us. Okay? In this course, there will always be a solution, okay? But if you find that your feasible set just keeps going out into infinity, blah, 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 infinity, infinity, right? Then it is possible that there are no optimal solutions, right? There's no way to minimize this thing, But for us, there always will be. Yeah? Okay. What does a minimization problem look like? Well, something like this. At a university, Professor Simmons, I don't know, wishes to employ two people, John and Mary, to grade papers for his classes. John is a graduate student and can grade 20 papers per hour. John earns $15 per hour for grading papers. Mary is a postdoctoral associate and can grade 30 papers per hour. And Mary earns a little bit more money because she has more education. Mary earns $25 per hour for grading papers. She's also a pastor. Each must be employed at least 1 hour a week to justify their employment. Now, if Professor Simons has at least 110 papers to be graded each week, so at least now, let's here. How many hours per week should he employ each person to minimize the cost? So when I'm going to bump this down and give myself another line just right away, because what's the first thing we need to do? X and Y, where X represents, okay, we're told to minimize the cost. And so that's our clue. So our cost, okay, I can look at the cost, which I know is $15 per hour for John and $25 per hour for Mary. So then X must be John's number of hours and Y must be Mary's number of hours. So X is John's number of hours. Oops. And Y must be Mary's number of hours.
Okay. If I switch them around to X and Mary, number of hours and Y and John, is that completely messy?
No, because as long as you keep this as your x-axis and this as your y-axis, right? If you mix those two up, then it would mess it up, and I would follow through as best as I can. But no, it won't affect anything, and that's why I like it as a question, because it doesn't really tie into anything except understanding the problem or showing me that you understand how to read these problems. Right. Okay. Nice. So what are these constraints then? 20x plus 30y. Well, that looks like the total number of papers. Right? Now that we're a little bit more familiar with these constraints, right? So we can confirm John can grade 20 papers per hour. And okay, so 20x, that makes sense. And Mary can grade 30 papers per hour, 30y, looks good. And then we have the constraint that there are at least 110 papers to grade, right? And so that's why it's greater than or equal to 110. I'll highlight that. But this is the number of papers. There are no other constraints, except, sorry, I said that and then I saw them. Usually it's x is greater than 0, y is greater than 0, but here it's x has to be greater than 1 and y has to be greater than 1, because each must be employed at least 1 hour a week. And so at least 1 hour per week each. Explain those two. Okay. So then, those aren't too bad, right? Drawing those lines, there's only 3 lines. My purple line is the 20x plus 30y is equal to 110. My black line is at x equals 1. And my red line is at y equals 1. I'll try to. Purple is at 20x plus 30y is equal to. So now the xy axis is probably going to be excluded, but how can we check? Well, I want to pick a point, right? And just from what we know about what I just told you about minimization problems is this area here will likely be the feasible set. So I'm going to pick a point in this region, right? And if all the constraints are satisfied at that point, then I'm right. So what's a nice point to use? Well, we could use 4, 4. I like to use simple points. And if they match, that's nice too. Bless you. As a test point. Or if you feel comfortable looking at x is greater than or equal to 1 and saying, okay, well, x equals 1 or greater, right? That's what points this arrow to the right, right? Y equals 1 or greater, that's when I'm up above. And 20x plus 30y has to be greater than 110, which means I'm now above the line, right? And so I already have this kind of idea about what my feasible set is, but we're just confirming. Okay? So let's see here. I need pages. Page. Let's start with the 20x plus 30y has to be greater than or equal to 110. If I'm using x is 4 and y is 4 as my test point, I want to know if it's greater than or equal to 110. 120 plus 80, 200. I think. Yeah. 200. Which means that, question?
Like, how come you do if there's a point like 20x plus 30y? How come is it 24 and 6?
The 4. Do you mean these 4 and 6? It will cross there, but we're restricted by y has to be greater than 1 and x has to be greater than 1. But it will cross here and here. But they're not exactly at 4 or 6. It'll be kind of slightly off. Yeah. Nice. So then we know on this line, I have to be above it, right? Just as we suspected. Now for the easy ones, if x is 4, so x has to be greater than or equal to 1. Well, I chose 4, which is greater than or equal to 1. And y has to be greater than or equal to 1. Well, I chose 4, which is greater than or equal to 1. So that test point is in the feasible set for all of these lines. So if I consider the overlap, let's see, where is my region? Well, I can go all the way down to here, down, and over, and then it goes all the way out. And it extends out to infinity, infinity. But like I said, minimization problems often only have a few vertices. So that's nice. Where are my vertices? Well, here, I mean, technically this goes to 1 infinity, and that's not going to minimize anything. So don't bother, right? But I will stop here, and I'll call this A. And then I see another one here, I'll call this B. Now, technically, it keeps going to infinity 1. But again, when x is infinity, I'm not going to minimize anything, right? And so I don't want it. So really, we only have 2 vertices that we need to find. A and B. Okay. And the vertices, A is the intersection of x equals 1 and 20x plus 30y equals 110. If x equals 1, I get 20 times 1 plus 30y is equal to 110. 90 divided by 30. Wait, I'll get there. Must be 30. We can use the graph to confirm that this intersection is at 130. Just pretend you didn't see that. Zeros aren't anything. I'll try my luck with the next one. What's vertex B? It's the intersection of 20x plus 30y and y equals 1 now. So B is the intersection of 20x plus 30y is equal to 110 and y equals 1. 20x plus 30 times 1 is 110. 80. I get 20x. I'm going to try to do this properly. 4, not 40. Good thing I was able to check with my graph. So the intersection should be at 4, 1. 4, 1. Good. Looks good. Now we're ready to evaluate the objective function at these two vertices. And so the vertex, the vertex for A was at 1, 3. And for B was at 4, 1. And I wanted to minimize the cost, which is 15x plus 25y. 15x. Is it 15? I thought he could do more. Oh no, it's the cost. Okay, yeah, sorry. Sorry. 15 times 1 plus 25 times 3. Oh boy. 75, 80, 90? It's a good exercise for me, but it's way too late in the day for me. Math is a morning subject. I'm used to morning classes. 15 times 4 is 60 plus 25, 85. Now remember, we want to minimize the cost, right? You get to choose, well, it's going to cost you 85 or 90. I choose 85. Poor Mary gets no work. 1 hour. Yeah. Of course. I'll start writing maybe just my blurb here. Therefore, the cost is minimized. Yeah, I can do it. Minimized to $85 by employing John for 4 hours and Mary for 1 hour. I'll do 1 hour. Sneak it in there. So they're basically the same. Right? Just have to remember at the end, if you want to minimize or maximize, you can look back at the question. And now, let's see here. Okay, doing good. You'll be happy to know that we only have one more example. This one, I think, is kind of interesting because we have maybe dietary goals that we want to hit. And so this is one way of solving problems like that. I think Professor Hamer is on a low cholesterol diet, but he's on a pretty weird diet. So let's see. But we've got pasta, we've got tofu, each with some protein, carbohydrates, vitamin C, and cholesterol amounts, right? And so these are things that we could have in real life, and you're setting up your diet. During lunch at the college cafeteria, he always chooses between two meals, pasta or tofu. The table below lists the amount of protein, carbohydrates, and vitamins each meal provides, along with the amount of cholesterol he is trying to minimize. So he's trying to minimize. Now, these days, you're probably trying to maximize your protein or something like that. But here, we're trying to minimize the cholesterol. Mr. Hamer needs at least 200 grams of protein, 960 grams of carbohydrates, and 40 grams of vitamins for lunch each month. Now, that's the funny part, because 200 grams of protein in a month is not enough. I'll tell you that right now, it's not enough. So that's why I think it's so funny. I guess it's just for lunch, but anyways. The rest of the time, he's just having a bunch of chicken breasts, I guess. Over this time period, how many days should he have the pasta meal, and how many days the tofu meal, so that he gets the adequate amount of protein, carbohydrates, and vitamins, and at the same time minimizes his cholesterol intake? Okay. There's a lot of information here, right? Luckily, I give you the objective function and the constraints. Okay. And which will save us some work. Give myself another line here. Okay. So just by looking at the table, I think you can guess which is your X and which is your Y, right? And also from the question, we were asked, okay, well, how many days should he have the pasta and how many days should he have the tofu, right? And so X is going to be the number of pasta meals and Y is going to be the number of tofu meals. So where X is the number of pasta meals, because I'm looking at the cholesterol, and it has 60 milligrams for the pasta plus 50 milligrams for the tofu, right? And so that's where my clue is of my X and Y. Of pasta, and my Y is the number of tofu meals. Okay. So then we were given goals for the protein, carbohydrates, and vitamin C, right? And so those should be our constraints, but let's confirm. So Mr. Hamer needs at least 200 grams of protein, 8x plus 16y has to be greater than or equal to 200, right? So that's my protein. We needed 960 grams of carbohydrates, 60x plus 40y has to be at least 960. So this is the carbs. And then finally, 40 grams of vitamins, presumably vitamin C, because that's all we have. 2x plus 2y has to be greater than or equal to 40. So then here's the vitamin C. can't have a negative number of meals, but you're allowed to have 0 of one of these, or I guess both technically. That would minimize your cholesterol. I don't think it's in the feasible set though. We can't have negative meals. Celery. Although I'm sure it's positive in something.
Out of curiosity, how did we get the greater than or equal to number of people right in the size for the first part? Because typically we've seen it and they've been the same on both sides, but now they're different.
So here, it's from this line here. Mr. Hamer needs at least 200 grams of protein, 960 grams of carbs, and then 40 grams of vitamins. So that's where those restrictions came from. Nice. Which is very difficult. If I didn't give you the constraints, it's very difficult to read this question, right? And figure out, okay, what is going on here? Yeah. How do you mean? So I'll give you, so you'll have the question, let's say like this, right? And I'll give you everything that's dark blue. Okay? Just like before. The light blue, you have to tell me. Okay? But everything up to here, I'll give you, right, in dark blue. And the question. Okay. Oh, and I guess I was pointing here on the whiteboard. If you're on the Zoom. Okay, can I do it with a tiny graph? I guess so. Because I've got a page break here, so I'm gonna have to stay here. Okay. I need to be above all these lines. Right? And so right away, I'm thinking, okay, I have to be above, right, above these lines, which is going to be somewhere over here. Right? Because we haven't done any work to find any of the intersections yet. We still need to do that, but let's find the test point so that we can find our feasible set. What's a good test point? I don't know. 2020 is in here. That might be nice. Before 2020, I had got this photo album to keep receipts in, so it wasn't like meant for photos. But it said 2020, the best year ever. And so now I think it's just really funny to have a photo album like that. Because it wasn't that great, was it? Although I got to stay home, so it's kind of nice. But it was weird. It was weird. I haven't been using orange, I've been using pink. 2020 as a test point. Okay, maybe I'll do my test point work over here. So for the light blue line, 8x plus 16y, it has to be greater than or equal to 200. Uh-oh, 20 and 20. 8 times 20 plus 16 times 20. I don't think I can do it, but I'm feeling pretty good that it's greater than 200. 16 times 20 is 320 plus 8 times 20. I get 480, which is greater than or equal to 20, which means that that was this blue line, right? This first line here. So then that test point is in my feasible set. I suspect all my other arrows will be pointing up as well, but let's confirm. So I've got 60x, plus 40y. It has to be greater than or equal to 960. Again, at 20, 20. Oh boy, 40 times 20. I think I did something weird. Oh, I did times. I get 2,000. Does that check out what you guys got? It's greater than or equal to 960. So that's good. And that was the green line, which means my test point is in there. And then finally, I have 2x plus 2y has to be greater than or equal to 40 at 20 and 20. 2 times 20 plus 2 times 20 is equal to 80. Yep, which is greater than or equal to 40. So that one's good too. Yeah. Anything that's in the region that you suspect would work. I just have a hard time doing math with 15. Find 20 is easier. That's all. Okay. So that means that it's confirmed. I feel comfortable picking my feasible set. I am going to incorporate x has to be greater than 0, which means I'm on this side of the y-axis, and y has to be greater than 0, which means I'm on this side of the x-axis. So all of those things considered, it looks like I am still in this region. And if we go ahead and start along the y-axis there, notice that that creates a vertex. Right? I almost chopped it off there. And then I go down, another vertex, another vertex. Oops. Oops, I went too far. Another vertex. Those are tight, but they're there. So now I'm going to start at the top and work my way down by labeling them. Call this A, B, C, and D. Send me home. Thank you. And, of course, the feasible set goes all the way out here. Okay, let's do this thing. We have to find the vertices. Find the vertices. A is the intersection of, let's remind ourselves that the y-axis is at x equals 0 and the x-axis is at y equals 0. Besides that, we have everything we need is at x equals 0, and I have to really squint. It's going to be hard to see on the screen, but trust me when I say it's the green line, which is this middle one here. 60x plus 40y equals 960. It's the intersection of x equals 0 and 60x plus 40y equals 960. If x is 0, that's a nice clean intersection to find. So then I have 60 times 0 plus 40y is equal to 960. Uh-oh. 60 divided by 24. And does that look reasonable, 0, 24? It does. Is the intersection, and again, it's going to be hard to see here, of the purple line here, which is 2x plus 2y equals 40, and the green line, which is 60x plus 40y equals 960. Uh, 2x plus 2y equals 40, and 60x. Oops. I'm going to solve for x in 2x plus 2y is equal to 40. I think this one, sorry, yeah.
For this, like the thing like when you have two equations, you taught us with the substitution where the equation equals y, which then equals y. The equation.
Yeah.
Can you do something like that here, like the 2x plus 2y equals 40 equals 60x plus 40y equals 960?
As long as you force them to be equal to each other. So one thing that you could do, if you wanted to, is you could move 40 over to this side, to the left-hand side, so it's 0. 960 over to the left, so subtract 960, and then that would be 0. So the only way that you can do that is to have them be equal to the same thing, and then you set them equal to each other. I think the elimination method would be easier for this one, but I'm stuck in my ways. Can try it. Should find the same answer. So I'm solving for x, so I get 2x, wait, try again. 2x is 40 minus 2y. Once I divide both sides by 2, make sure that you get 40 minus 2y is all divided by 2. Now when I split this up, I get 40 divided by 2, which is still nice, 20. And then minus 2 over 2, which is just 1, so then I get minus y. So I did kind of glance ahead to make sure that it would still kind of give me a nice line. And then I'm going to substitute into 60x plus 40y equals 960. This x is going in here. So I get 60 times 20 minus y plus 40y equals 960. Expand that 60, and you get 120 minus 60y plus 40y is 960. You simplify by moving the 120 over to the right-hand side, and you have negative 60 plus 40, you get negative 20y is 960 minus 120, which is 840. That doesn't make sense. Why did I get a... I'm expecting something like 812. Where did I go wrong? Oh, haha, nice try, Emily. 60 times 20 is not 120. I'll sneak another 0 in there. That's why. Sorry. And then 960 minus that. There we go. Whew. Now I get y is 12. And x is 20 minus y. So x is 20 minus 12. X must be 8. So then the intersection is at 812, which matches where roughly where I was expecting it to be. Okay. We're in the home stretch. C. C is the intersection of the purple line and the blue line. Let's see here. I'll just copy these so that I don't have to scroll around so much. And I want the purple line and the blue line. That's just for me. I'll delete that in a bit here. So C is the intersection of who phone, who dis, 2x plus 2y is equal to 40, and 8x plus 16y is equal to 200. Lots of ways you can solve it. A nice contender could be elimination method, if you like it. I'm going to stick to my usual. Solve for x in 2x plus 2y is equal to 40. So then I get 2x is 40 minus 2y, which we already saw is 20 minus y. We're going to substitute that into 8x plus 16y equals 200. Substitute into 8x plus 16y equals 200. 8 times 20 minus y. 16y is 200. Okay. Don't forget any zeros, Emily. 8 times 20. I know. 160 minus 8y plus 16y is 200. 16 minus 8 makes 8y, which is 200 minus 160, which is 40. So y is 5. Checking. Oh, and then so x is 20 minus y. 20 minus 5 is 15. We can check that 15, 5 makes sense on our graph. looks good. Our last vertex is easiest one, I think, or one of the easier ones. It's the blue line. 8x plus 16y is equal to 200. It's the intersection of 8x. Oh, now I've lost it. Blue line. 8x plus 16y equals 200 and y equals 0. There we go. 8x plus 16 times 0. That's nice. I get x must be 200 divided by 8. It's 25. And we already know that y must be 0. We'll confirm. 25, 0 doesn't make sense. 25. Well, I drew over it, but I feel pretty comfortable with 25, 0. Okay. Hard part. Done. And it's not even that bad. Now, we can set up our table with our vertex, A, B, C, D. From above, I see 25, 0, 15, 5, 8, 12, and 0, 24. Moving up. Now, we bring in our objective function, which we've ignored. We want to minimize, and remember, you want to minimize the cholesterol. So, which is 60x plus 50y. So we have 60 times 0 plus 50 times 24. 50 times 24 is 1,200. How about the next one? 60 times 8 plus 50 times 12. 60 times 8 plus 50 times 12. That's better. It's lower. We want to minimize. 60 times 15 plus 50 times 5. Here we go. 60 times 15 plus 50 times 5. Not as good as that second one. 1150. And then finally, 60 times 25 plus 50 times 0. Ooh, that's a bad one. 25 pasta meals. Probably not. In theory, I guess you would have an upper limit on the number of meals that you would eat at the school, but we'll ignore that. Maybe he goes to work and eats every day. So what's the minimized? I'm gonna go for B. This is our minimum. Therefore, his cholesterol is minimized to 1080. I don't know the units, and I'm not going to scroll all the way up there. So 1080 grams. Thank you. when he has 8 pasta meals and 12 tofu meals per month. Eight pasta meals and 12 tofu meals per month. Oh, did it. Bless you. That is the end of chapter 3. And so for Monday, we're not meeting, no class. I'll post the video. I'll send out an announcement when it's posted. So then you can watch it whenever you'd like. And then I'll see you a week from now on Wednesday. Enjoy your hopefully extra long weekend or something like it. I release you.